Good morning. This is a continuation of the previous session on the probabilistic method of power estimation, what we had discussed. To recall the basics, when we go for having any particular node with a capacitance of C switched over to VDD to represent a logic 1 state and a 0 volt to represent a 0 state running at a frequency of F would incur half CV square times the frequency during charging and the same amount during discharging, and we through this topic would determine the frequency of such switchings in a probabilistic manner. The statistical theory, how we are going to be helping it. The basics we had seen on the other day itself. Now we would go for some definitions and the concepts behind which leads us to the theory of defining the transitional probability, and based on that the frequency, how we are going to be having. That would be the focus of our approach now. First would be the static probability, and because of that how we would go for having the frequency of the switchings what are happening. This would be defined as the time for which we would define the static probability of being at 1 as P, and this would be the ratio between the time duration for which the signal node is at a logic 1 state to the total time what is under observation. Naturally, the total time t is going to be t0 plus t1, that is when the signal, when the logic is at a 0 level and this at a 1 level, the total time is going to be the observation time, and out of this observation time how much is going to be at the 1 state. If I call this as P of 1, naturally I would be representing, for the other case I would call this as a P1, then I would have P0 to be defined as the remaining time, that would be 1 minus P1. Now with this idea, if I talk about the probability, it can never be a 0 or it can never be a 1. It has to be somewhere between 0 and 1. That means if the probability is 0, that means that I don't have the signal existing in the logic 1 state at all for any point of time. And similarly, if I say that the probability is 1, that means it is always at 1 and there is no time for which the signal is at 0. Therefore, this sort of a representation for the probability, it could take the values between 1 and 0 as the two extremes. This would be like go for taking a 10,000 toss experiment with a coin and go for identifying the maximum heads and tails. That would be, normally we have them to be around 0.5. That is what would be the value when I go for a single coin. I take the single coin and I toss it, and I would be getting this sort of a probability happening for the heads or the tails. Next we will talk about the conditional probability. That is, we know the probability of being at 1, we have taken that to be P, and the probability of being at 0 is P of 0, that is given by 1 minus P. And in this case we assume the tossing of coins is memoryless. You don't have the state of a particular state influencing the next state. It is memoryless, completely memoryless. So in this conditional probability we would assume two coins. One coin would be assumed to be for representing a 0 state and another coin to be representing a 1 state. Now I would go for finding out the independent variables to represent the tossing of both the coins together. If I take the 0 coin and toss it, I may get something. It could be either a 0 or a 1. And if I take the coin representing 1 and toss it also, once again I would be getting whether it's a 0 or a 1. Using this, actually this we are going to be calling it as a log 1 model. And in this model, what we are going to be having is, if the current state is at 1, if current state is 1, then the probability of the current state being 1 switching over next to the 1 also is P, and similarly if the current state is P of 0, the next state, it could either be a 0 to 0 state only, or the 0 state could have been got through from P current state being 1 and that to the next state being a 0. That means when I talk about P of 0, previously I would have been at a 0 and I would have remained at 0, or previously I could have been at 1 and I could have switched it to 0. So this is going to be 1 minus P. And similarly I could put for the P of 1, that is going to be previously I might have been at a 0 and would have switched it to 1, or I would have remained there previously also at 1 and I would be going to the same once again. So this also is going to be P. This information with respect to the current state being something, with respect to that the next state changing, we call them as the conditional probability. The next one what we would go for talking about is the transitional probability. When I talk about the transitional probability, we have seen previously how the transitional probability is going to come into the picture because of the presence of the clock in our digital circuits. So whenever the clock boundary is happening, along with that if I go for getting a transition, I say that it is the transition happening at the particular clock edge. So I would go for taking that as a transitional probability, and this transitional probability T would now be, I should have my transition happening if it was previously at 0 and switching over to 1, or the transitional probability that the current state is 1 which is going to be switching over to 0. And we know from the previous page that the transitional probability T01 is going to be there only if I had my 0 existing, that is P0 existing, and if there happens to be a 0 to 1 state, state change, that is it is P01, only then my T01 would be there. And similarly if I want to have a T10, that means previously I should have been at a 1 with a probability of P1 happening, and this to be changing over to 1 to 0, that is P1 to 0. And this we know P0, we know 1 minus P, and this P1 is P. So simplifying this, I would get twice P times 1 minus P. If I have this as a transitional probability, I would want to know at what frequency my circuit is changing it out, at what frequency my node, a particular node state is changing it out. So that would be equal to the capital T divided by 2, and that would be P times 1 minus P. So this is what I call as the relation between what we have as a probability and frequency F. To elaborate this further, we will go for taking the 4 variables what we will have. 4 variables what we would go for considering. What are they going to be? P of 0 to 0, that means previous state being a 0, next state being a 0, and P of 1, 0. And then the next one is P of 1 to 1, that is the current state being 1, next state also being 1, and P0, 1. These are the 4 states. And we know P of 0 to 1 with the current state being a 0 switching over to 1 plus P of 0 to 0, the state being remaining as it is, both are equal to 1. And similarly P of 1 to 1, the state 1 remaining as it is, plus 1 to 0 to be equal to 1. Because it could either be at this state, or this state and this state, totaling 1 at 1 each. Now the static probability of P0 we know as 1 minus P1. And P1, I would go for defining that as the sum of, it could have been at a 0 and it could have changed over to 1, or it could have been at 1 and it remains at 1. Similarly, I could have this written as for P of 0, I substitute 1 minus P1 times P01 plus P1, P11, and this, if I go for simplifying, my value would be P01 plus P1 times P11 minus P01. I take this P1 and this P1 together. I go for defining P1 as P01 divided by 1 minus P11 plus P01. That is the probability of remaining at 1 in terms of the conditional probabilities we have found out. And I would go for taking in the similar way P of 1 1 plus P of 1 0 is naturally 1. That means the current state, with the current state as 1, changing to 1 and changing to 0 is 1. This also implies that P1 1 is going to be equal to 1 minus P1 0. From this I derive. Therefore, I will have P1 to be equal to P01 divided by 1 minus 1 plus P10 from what I have derived in the previous page, P01. Now this is equal to P01 the whole divided by P10 plus P01. Here I have the static probability, and we are able to find this from the conditional probabilities. So given with the states as P01, P00, which is the first set. Next state could be P11, P10, and the third set as P1, P0. We could go for defining any particular state, the probabilistic conditions. Using them, how we go for calculating the transitional probability from these 4 variables. We have seen that T is what? P of 0 we have defined already, P of 0 and changing over to 1 plus P of 1 changing over to 1 to 0. This is what is the maximum transitional probability. And I go for substituting for P0 and for P1, and I have everything only in terms of the conditional probabilities. That would be equal to P10, P01 divided by P10 plus P01 plus P01, P10, the states changing, divided by the same P10 plus P01. This becomes equal to twice P01 into P10 divided by P10 plus P01. Therefore, we know F is equal to T by 2. Therefore, P01, P10 divided by P10 plus P01 becomes the frequency, and this is nothing but from the previous substitution P1, P10, the same is equal to P0 times P0 to 1. And when we go for having, P0, 1 is equal to P10, that is when it is 1, the maximum could be what? 0 to 1 sequence changing. And F could be at a maximum 0.5 only, because if I go for drawing the frequency, I go for drawing, this is P, the frequency and the probability. If I go for comparing, I will take this as 0.5. If I have P, the transition is going to be P times 1 minus P. That's what is going to be the maximum what's happening. If I have 0.5 as P, then 0.5 into 0.5, that would be 0.25. And if I go for taking probability of being at 1 is more and the probability of being at 0 is less, it's going to be 0.8 into 0.2, which would be 0.16 only. So for no other values other than this 0.5, I would have the maximum frequency happening. Therefore, the frequency, if I plot, the maximum would be happening at 0.5, and that would be the 0.25 frequency for the F value. With this particular idea, now we go for switching over to how we will have for a word level. We have been talking about the bit level, the probabilistic theory. If I go for considering word level and bit level statistics, this is to give you idea about how this information is going to be helping us for word level data streams, what we would be processing in any architecture. For example, adder, any particular multipliers, memories, wherever I go for having words of data entering, and the bits are going to be changing, and how do we go for taking them. Any particular value in a word is represented by, for I is equal to 1 to n minus 1, for n bit data, bi 2 power I. Therefore, each of the bits of the particular word of the length of n bits in each word, if I go for considering them, I represent like this. Now, any particular bit in this word, if it is going for changing from 0 to 1 or from 1 to 0, if I know the probability of each bit pi changing across the whole sequence of operations, and if I am able to sum it up for each of the 0 to n minus 1 bits of all the bits in the word, then I have a way to find out the power dissipation in the particular set of words and the transformations among the words. Therefore, I could define this as, for all the integer w, what I have, p of w each word, and in which I have the ith bit of each word to be a 1. And if I go for having this information, naturally I know when each bit of a particular word, and for all the words they are in high state. I know when they go for switching, I will know the transition probability, I will know, and I would be able to have the power dissipation done. We haven't actually talked about how the power dissipation ultimately is going to be taking power dissipation is going to be measured, but we are right now talking about how the static probability is helping us, how we are taking that over to the conditional probability, how the transitional probability is coming into the picture, and how we would go for making use of the bit changes conceivable from even a word level statistics. We have seen that. Next, we will go for the probabilistic power analysis techniques for digital gates, for simple gates. This is what you see. I am showing a particular segment of a particular circuit. I have two gates, and I have these to be, I will call them as internal nodes, and these are your input nodes, and I have my final output node for this particular segment of a structure. And each of the inputs I have for a probability of P1 with a frequency of F1 happening, P2 with a frequency of F2, P3 probability for this particular input with a frequency of F3, and these are the primary inputs for this particular module. And I have the internal nodes as I go from left towards the output, from input to output, as I traverse across the whole thing, the internal nodes, whatever intermittent nodes I get, their values, the probabilities and the frequency of them happening would naturally be dependent on what I give at the input. Corresponding to that, what it changes. From that, it travels down to some more stage and finally to the output stage. Therefore, I know for any particular digital logic, I would go for identifying the transitions, and based on the transitions, with the idea about the probability of each input, with the frequency happening, through the nodes how they transform, and at the output I can define the pk and fk value, and we are now in a position to next understand how each of these gates, the Boolean functions, would go for operating with respect to the static probability. That is what is the next item what we need to study. Even if I go for taking a very simple transistor, I go for giving this input, this gate with a certain logic signal, and I go for taking the output from here. So from the input to the output, I go for transition, I go for sending the response from the input to the output, and how we go for having the output modulated by the input. With that idea, we will have all these digital gates, the theory of the digital gates helping us to go for the static probability, how they go for propagating through the logic circuit to the output. That is what we would see in this continuation. We go for considering the simple gates. This is an inverter. If it is P1, naturally it is going to be at P of 0. That means which is at P1 minus P1. And similarly, if it is an AND gate, we know both the P1 and P2, the probability of P1 and at the same time the probability of P2 happening. That would be for the AND gate. And for the OR gate, we would take either P1 could be present or P2 could be present, and both can be present also at times. So I will have P1 plus P2 minus P1 P2 to be that for your OR gate. With this information, I would go for considering any particular logic signal with certain inputs happening through the circuits. I go for through the gates, the Boolean functions, whatever I have implemented, I will have the data passing through, their probability, their transition frequency, everything reaching the output. There I measure. So if I want to have very accurate calculation of the power, naturally I could traverse it across each of these input paths to the output and identify. This method, how is it working? We would, it's to summarize the idea. The input is given with all the signal probabilities for all the inputs to the circuit, and I get the output as the signal probabilities of all the nodes of the circuit. And for the procedure what we will follow, as I said, we would summarize once again here. The step 1 would be for each input signal and gate output in the circuit, assign a unique variable to identify, and starting at the input and proceeding to the output, take down the expression for the complete output of each of the gates as a continuous sequence till you reach the output, and for their probability you substitute and find the output, and you will assume they are mutually independent primary input signals only, because we are considering memory-less model, naturally strict sense stationary, mean ergodic, and therefore we are not actually having one data to be in any way correlated to the next data. And in this process, we would have even exponents formed into each and every node, many of the nodes. In such cases, you go for suppressing all exponents, because I may have one particular input, this may be traversing through one path, and the same input traversing through another, and I may have my exponent here happening. And this way, I would go for having suppressing all the exponents would help me to obtain the correct probability for that particular signal. And this is for convergent and reconvergent nodes, what you might have studied in digital theory. The idea about that would help you here for your clear understanding. and how the probability, the static probability, is going to be propagated through simple circuits, and how we are going to be taking the help of Shannon's decomposition for our theory. This is what we will continue next. This is a very simple gate, AND gate. As you see, I have probability of P1 and P2, and the probability of the output being at a 1 is equal to P1 times P2. And I would want to know for each of the input, I would want to consider whether this has its effect at the output. How do I do that? With respect to this Shannon's decomposition, we will go for explaining about that. We will consider a function y is equal to f of a Boolean function of so many variables x1, x2, xn, etc. Out of this, I consider for our understanding only xi. I now find out what the effect of xi bit is on the y. That means the influence of a particular input xi being at a 1 or at a 0 on the output. I have my output. This output is determined by the input bits, and how exactly each of the bit, whatever I have here, is influencing the y. That is what we find out from the Shannon's decomposition. It rather helps us very nicely. How I do this output, particularly for the input xi, would be defined by xi times fxi plus xi bar fxi bar. That means fxi and fxi are the Boolean functions obtained by substituting your xi with a 1 here and with a 0 here. That means the y I would want to check with a particular input applied with a 1 condition and a 0 condition to check the influence of the output. Therefore, y is, you are keeping your xi function at logic 1. What is fxi with xi at 1? What is fxi bar with xi at 0? This is what we are doing. So fxi and fxi bar will not naturally have your function xi. Other than that, the remaining variables will stay. Now if I go for simply finding out the probability of this to the probability of the output, then what would I get? The probability of the output y to be present with respect to a particular input would be the probability of xi times fxi plus probability of xi bar times fxi bar. And what is this? P of xi times P of fxi. And similarly here, P of xi bar into P of xi bar. Therefore, the idea about the output probability with respect to each of these inputs and the change in each of these inputs, how they reflect on the output, we have now found a way. And using this, we will go for taking one example. In this example, I would consider a Boolean function y is equal to ab plus c. And I would also consider PA, PB and PC to be the probabilities of all the three inputs. I would want to know what is the output probability P of y. Now from the equation what I am having, P of y naturally will be equal to, I would first take A to be your xi and probability of A, that is I am putting 1 for your function, and what is the fxi, if I put A to be 1, that would be P of, with A as 1 I would have P of 1 dot B, that is B plus C, plus I would go for putting for the same a 0 value, that is xi bar I put. So P of A bar, if I put P of A, this one for A, if I put 0, naturally A dot B would go for 0. Therefore, it would be P A bar multiplied by P of C. So this is equal to, I have an R function here, therefore P of A times PB plus PC minus P of B times P of C plus I have here a P of A bar, which is going to be 1 minus PA times PC. Go for simplifying this. PA PB plus P of A P of C minus P of A multiplied by P of B multiplied by P of C plus I have here the P of C minus P of A times P of C. Now I have P of AC here, P of AC here with a positive and negative. I get it cancelled. So I would now have P of A into P of B. This is what our P of Y is, minus PA, PB, PC plus P of C. This is what is the output probability, taking into account the input probability. For any such circuits in this manner, we could go for taking out the output probability measured. Next, we would go for considering something, a continuation. This is not enough that we find about the probability only. We would want to know how the transition density, how frequently it changes. That we are going to now introduce into this. The probability we have understood. Next would be the transition across each of the gates, how it would go down to the output from the input. The transition density signal model in this would make you understand what it is. The transition density signal model, actually the work by Najam, a major work, and this actually is a very considerable contribution for the study about the transition density signal model. He defines the transition density and the static probability, how they are actually, they can give the complete information about the signal, how we can go for efficiently characterizing the logic signal. In this regard, we will take examples of 3 different transients. This is at logic 1, and here also it is at logic 1. So much of time of observation what we have taken, out of which we can mark the probability of being at one state as 0.1 plus 0.3 units of the time, so it is 0.4, and within which it incurs 4 such transitions, therefore 4 toggles per second. Given with the transition density and the probability, we will be able to know what the P0 would be and what the frequency would be. The complete entire information about the logic signal can be obtained with respect to, and this signal, if I go for taking, this also is probability of 1 is 0.4 and the 6 toggles per second it has, and this 2 you have. And for example, I will take another case where the transition density is given as 0.1 and I have the probability P1 to be 0.4. In such a case, I go for considering to measure. I want to measure how much would be P1 to 0. If at all I have the logic high probability to be 0.4 and the transition density, if it is at 0.1, if at all there is to be a transition, then I will be able to know how the probability of 1 to 0 will occur just from these 2 data. And the 0 to 1 and 1 to 0 transition gives me the frequency. Therefore, from the information of P of 1 with 0.4 and the transition density of 0.1, I will now be able to define P of 10 as equal to T divided by 2P1. And this is how. Similarly, I could take another case. If I know P of 0, 1 minus 0.4, 0.6, given with 0.0 for the P0, then that is I said 0.6 as the probability of P0, then I will be able to know, given the transition density, what is the probability of P01 occurring. This is how, T divided by 2P0, and I go for measuring this. Therefore, these sort of informations would give you information about the logic signals. Now, the propagation of transition density we have seen already, and we will go for just recalling them. For the Boolean function, y is equal to f of x1, x2 up to xn, and I go for calculating the static probability p of xi, and I know, and I would go for having the transition density for each of these signals, and we would be able to, with the use of the probability of y what we have for the particular output, and given with the transition density of all the input variables such as my xi, whatever I have, I will be able to measure the static probability and the transition density this of the output variable what we have in response to each of the inputs whatever we have in the system. That is, we would have the input variables, so many numbers. For them, the static probability at the input we know, and the input variables, whatever be the transition density, we know. Using them, we will identify what is the probability of the output and the transition density at the output. Using them, how we would go for the power measurement ultimately. That is what would be our next attempt. And this is another example what we would go for considering to understand whatever we have been studying so far. This I would take the same example what we have taken before, y is equal to AB plus C, and given with the function we have the values, the P of A is given, probability of B at 1 is given, probability of C is given, and the transition density of A, density of B, density of C also are given. I would want to now compute the transition density and static probability of the output y, where the logic function y is equal to AB plus C is given. First, we would identify what is the probability Py. From the previous example, we had calculated, we had worked it out. Pa into Pb. I will take the same answer from the previous case. Pa, Pb, P of C plus P of C, that is what we had obtained, and I will go for substituting for each of these the values what I have in the problem. 0.2 into 0.3 minus 0.2 into 0.3 into 0.4 and plus 0.4, that would be 0.484. And now I would want to compute the transition density. Probability we have calculated to compute the transition density. Compute the transition density. Now I would want to calculate the Boolean difference functions. Find the Boolean difference functions. We would have a discussion on the Boolean difference function before continuing with the current example. We have, let us recall the Shannon's decomposition. Y is equal to xi fxi plus xi bar f of xi bar. In this, as you can see, the output can happen either with this or with this. If at all the xi has to have any influence over y. That means if xi is 1, it will have certain fxi and it will reflect here. Otherwise, if xi is 0, it may have an influence on fxi and it would have y to be affected. So only two situations I could have. Either fxi can be 1 and fxi bar can be a 0, because if at all xi has to have influence on y, this should happen. Fxi will be 1 and fxi bar is equal to 0, or other case could be there also. What is that? Fxi could be a 0 and fxi bar can be a 1. Only these two could be happening. That means what? I can combine this as fxi XORed with fxi bar can be a 1. This is what I am going to be calling this as Boolean difference, and the dy by dxi, the difference function for each of the inputs whatever we have. That means the input transition at xi will have an effect on the output. That is, it will propagate to y. That is what it means. Propagate to y. That is, it will happen only if my dy by dxi is equal to 1. That is either fxi or fxi bar or 1, but not both simultaneously. You can actually think, if I have a fxi and also fxi bar to be 1, that means it doesn't make any difference on y whether xi is a 1 or a 0. That's what it is. It is simple. This information is now going to be used for the example what we have taken previously. We will continue with the example what we had. I calculated the probability of py, and then we would want to now calculate the Boolean difference functions with respect to each of these inputs. First we would go for taking a dy by dA. I am going to be putting for a 1, and I would be putting for a 0, and I would calculate fxi and fxi bar. That would be what? Fxi would be putting 1 for a, b plus c, XORed with putting a 0 for a would now amount to 0 dot b plus c, so plus c only, and I go for expanding the simple exclusive ORing b plus c bar c plus b plus c, c bar, you expand, you will find b, c bar, and the probability of the same, if I go for taking the probability of dy by dA, would now be probability of b times probability of c bar, or I could say this probability of b times 1 minus p of c, and all these factors I know from there at the top. So p of b is 0 times 1 minus p of c, 0.6, so it would be 0.18. Similarly, I would go for finding out for dy by dB. Now I would make b to be 1 and a 0, calculate fxi and fxi bar correspondingly, and I would have here a plus c XORed with, because b I am putting 1, XORed with the c, and I would have a c bar, and this would be for probability if I go for calculating p of dy by dB is equal to p of a times 1 minus p of c, and that would amount to 0.1. Similarly, I would go for calculating for dy by dc. For dc, if I put 1 plus your ab, that's going to be naturally 1, that would be XORed with ab, that would be ab bar, and a p of dy by dc would be equal to 1 minus pa pb, because it is ab whole bar, and that would be 1 minus 0.2 into 0.3, that's equal to 0.94. Now I would want to calculate the transition density. I hope you understand the logic behind this. Transition density for the output d of y, transition density d of y of output. D of y will be equal to, that is, we have found out the Boolean difference of the output with respect to each of the inputs, and then we know each of the inputs how frequently they are going to be switching. The transition density we know. So our job is now going to be simply multiply the probability with respect to each of those inputs, the probability of output happening, times the transition density. So it is P of dy by dA was from our calculation 0.18, that multiplied by the transition density of 1 plus dy by dB into d transition density of B is 2 plus your transition density of C multiplied by its probability. That gives you the final value d of y. Now we have found out at the output what is my transition density, and with this transition density how the power would now be estimated. That is we are reaching our final point. We know the power dissipation is dependent on the input probabilities and the transition densities and the Boolean function of each node with respect to the primary inputs. This is to summarize again. Input probability we calculated, we had using them, and the transition density is what is given. We had gone for finding out the Boolean function of each node with respect to the primary inputs, and we have the final, the process. I am summarizing once again: the Boolean difference, find the transition density dy of each node with respect to each of its inputs. That is what we had done for our inputs A, B and C. After having done that, my job is to measure the power, and we know d of y, that is how long that is going to be at logic 1 or 0 we know, how frequently 1 to 0 transition is going to be happening we know, and this output effect in total I am taking care of by d of y, and I know the load capacitance at the node y, I know the supply voltage, I measure the power, and this 0.5 dy is the frequency and cy is the capacitance at node y. This is how you measure the power given with such probability for the inputs and the transition density for the variables. In addition to this, we may go for extending this information, whatever we had been discussing, to calculate the signal entropy, which can be done in another session.